A unit vector is a vector with a magnitude of 1 and has no units, and as such only represents direction. A unit vector is indicated from a regular vector or normal vector with a hat symbol over it. A unit vector can point in any direction, and because they occur so often, the unit vector for each of the three Cartesian directions, x, y, and z, are given their own symbol. So I, for the unit vector pointing in the x direction, j for a unit vector in the y direction, and k for a unit vector in the z direction. So for simplicity's sake, we'll just look at a unit vector in 2D. It only exists in the x and y. And you can note that this unit vector is only 1, no matter where it's pointed, okay? And if it is pointed exactly at 45 degrees, so if theta is 45 here, okay, the value of the unit vector I and the unit vector j will be the same, okay, because it's at 45. If we move it entirely in the direction of, say, y, the value of the unit vector, okay, represented by f in the hat, is equal to the unit vector j, okay, because it's entirely in the y-axis. Same thing is true if we move it entirely on the x-axis, so it's 1. So if we apply Pythagorean's theorem to that triangle that we saw, and we have a radius equal to 1, okay, which would be the hypotenuse of that triangle, we would get the cosine square of theta plus the sine squared theta is equal to 1 squared, which is 1. And it's important to note that we're measuring this theta from the x-axis, okay? So if we were to flip it and measure it from the y-axis, we would have to flip the terms, okay? So x component, or the I component would be sine, and the j component or y component would be cosine, okay? But if we take the standard notation of from the x-axis, what we end up with is that the x component of that unit vector, okay, is equal to cosine of theta, and that the fy component of that component is equal to sine of theta. Let's look at this interactive example found in your text. Here we have where we can adjust the force here. Okay, now this is a true force vector with a direction and a magnitude, and it's represented by F. It has a corresponding unit vector here, okay, denoted by the hat on the F, okay? And as you can tell, the magnitude of this force is illustrated here by this dashed line here, okay? And it has a magnitude of 4 newtons. Of course, a unit vector has a magnitude of 1, and it's represented by this circle here. It always stays in that circle because it's only 1. Now, right now I have this at a 45 degrees. That means that the x and y component are the same. Please note that in the unit vector here, we have it described as cosine of 45, sine of 45, which are the same, which are 0.707, okay? So no matter what magnitude this is, it never affects the value of this. It only changes the unit vector components if you change the angle, okay? And also to get the corresponding f sub x and f sub y, you multiply the unit vector by the force. So 4 is the force times 0.707 yields 2.83, okay? And it's the same. So again, the unit vector will not change unless you change the angle. So here, now I'm going to change the angle, and I'm going to change this as best to 30 degrees. Okay, so now I've got it 30 degrees. And so it's changed the values of these unit vectors for I to 0.866, so it's much closer to my x-axis, so the I component is larger. The y component or j component for my unit vector is smaller, and same thing corresponds to the full vector component for x and y. So now my x component, f sub x for this is 2, and the f sub y component is 3.46. I'm sorry, reversed. 3.46 for the x and 2 for my y or j. Okay. All right, let's look at the example of force vectors from position vectors. So we have set up this problem where we have a and a B. The coordinate for A is 2, 3, minus 2.5. So that's the x, y, and z of A. The coordinate for B is minus 2.5, 1.5, and 2.2. A 5 kilonewton force is acting at A, and it is pointed at B. The first part of the solution for this is to find the displacement of that vector A to B. And to do that, we need to find the deltas between A and B in their x, y, and z components. We know the coordinates, so therefore we have all the numbers to calculate this. So we just plug in the coordinates for the x coordinate for B and x. Okay, so that's minus 2.5, and it's a difference, so it's a delta and a minus 2, so those add up. So the I displacement is minus 4.5. And we follow these and complete these for the y and the z. So we end up with minus 4.5, comma, minus 1.5, comma, 4.3. These deltas can be seen here in this drawing where we have, I've highlighted, these are the deltas. Okay. So again, we're starting from point A down here, and we have a delta for my x, which is along this axis here. So it goes back 4.5. Then it goes over minus 1.5. And then it goes up 4.3 to get to B. So these are the deltas we just calculated. The next part is to actually determine the magnitude of the displacement vector. And that is just simply your delta squared plus y, or your delta y squared plus my delta z squared, and the whole thing we take the square root of. And you probably recognize this from Pythagorean's theorem. And the result of that is 6.402. And this represents the distance from A to B. And if we check the distance of this line here, okay, that should be the magnitude of the displacement between A and B, and that's just simply the length of that line. If we check it here, we've got a length of, just like we did in the calculations, we got 6.402. And to find the unit vector, all we need to do is now divide by that magnitude of that line that we just found. So we're just going to say simply the displacement of our delta x, delta y, and delta z, and divide each one of them by the displacement vector, which had a magnitude of 6.402. And this reduces them down into their unit vectors. Okay, and again, these would come out to a force vector of 1. To find the force vectors for this, all we need to do is take our unit vector, which we found above earlier, and multiply it by the force that we have, which was 5 kilonewtons. Again, remember the 5 kilonewtons acts from A to B. We multiply this and we get our components, okay? So we got minus 3.51, minus 1.17, and a positive 3.36 kilonewtons. If we look at the graphical representation of these components, you can see them here. So this is the minus 3.51 in the x direction. Again, this is A. We're going to B up here, but that length of the line represents that. And then this is the y component, okay? And this is a distance of 1.17, and because it's going in the negative, or that direction, it's negative. And then the z displacement, which is 3.36. Direction cosines is a way for us to calculate an unknown directional cosine. So by using the equation 2.53, and we're setting it equal to 1 since it's a vector, and we're using the directional angles off of the x, y, and z, or I, j, and k. If we know 2 of them, we can always find the third. So let's look at an example of this. Here we have a force drawn in 3 dimensions. It is located 45 degrees off the z-axis and 60 degrees off the y-axis. So we're going to start with equation 2.53. And so that gives us a unknown theta x, but we also know theta y, which is 60, and we know theta z, which is 45. So solving for theta x, we get the square root of 1 minus cosine squared theta y minus cosine squared theta x. We solve for theta x and cosine theta x, and we get 0.5. Now, there are 2 possibilities that we can have, and one is that the value of theta x is equal to 60, or it can also be equal to 120. We get this by subtracting 180 by 60, okay? Now, by just inspection, okay, when we look at this, we realize that x has to be, the component for x is going to be in the positive direction. So just by inspection, we know that the value for theta x is 60. If it were 120, it would actually be a negative.